Hello, I'm Brian Corbridge, and this is my presentation on the lab reviewing constant velocities and Newton's second. I know this speedometer is moving up and down, but it should be constant because we're talking about constant velocities. For starters, we must get a clear understanding on what it means to have a constant velocity. When there's a constant velocity, there's no acceleration and no net force. We know it's because of Newton's second law regarding kinematics. If there were to be a net force, then there would have been acceleration, and we aren't focusing on that right now. In the following video, we will disregard the ball's movement as it descends down the ramp. We're only going to focus on when it reaches the flat stretch because that's when the velocity is constant. When it's falling down, there's going to be some acceleration. Here's the video I made for demonstrating the constant velocity. We're only focusing on when it reaches here and goes all the way over here. That's this whole time. Here's my preliminary position versus time graph I made for the ball's movement. You can see that it has a constant velocity by this constant slope, this linear slope. Um, and I decided to have the where the ball originally was at the origin, but say it started, 2 units. In this case, this is in meters per second. Um, well, the positions in meters. Say I started, 2 meters above that, it would, be up here and it would have the same slope. But I decided, to start at the origin, keep things simple. Here are my calculations I needed to do the graph on the previous slide. As you can see here, we have VF squared minus VI squared equals 2 acceleration times distance, and that distance will be the hypotenuse of the slope. Even though I said we were disregarding it, I just used it to find the velocity the ball traveling with when it hit the flat stretch. I used, gravity for acceleration, distance. I did some trigonometry, found distance. I found the velocity that it entered the flat stretch with was 1.85 meters per second. Forgot to mention this on the last slide, but that 1.85 meters per second was the slope for the position versus time graph. Um, Anyway, as we carry on, we can look at, I now plugged in the video into Tracer, put in this protractor, found like the angle and whatnot, use their measuring assistants and tools to find, vector and whatnot. And I will say it wasn't the most accurate thing. It gave me a distance of, as you can see up here, 325 meters was the length of this vector. Obviously, it's not. Um, there was a yardstick there, so it should probably be, a little more than a meter. But anyway, I used that to calculate the position versus time graph that you will see later on um, from this data I was able to collect from the tracer. In that last video, I just showed you me plugging in the values I was able to collect from Tracer. After time, I've made 0.7 seconds because that's how long it took for the ball to cross the beginning of the vector to the end of the vector in that flat stretch where the velocity was constant. Um, and because Vector or Tracer said that length was, I think it was like 600 something meters, I multiplied that by 0.7 for seconds to find the velocity. Well, technically, GlowScript did, but that's how they got that. Um, I know the it didn't really show the ball moving. I guess because the numbers are so wonky. Um, but that's fine. You can see the velocity versus time graph and position versus time graph. As you can tell from velocity, it's a flat line because it's constant, 887.9 meters per second, which isn't too realistic, but that's what we're going with because that's what Tracer gave me. Um, as you can tell from my predicted graph and my predicted values, it's way off. I think I'm a little more correct than Tracer because it is such a ridiculous number I got from Tracer, but it is what it is. Um, and so yeah, that's my presentation on the Constant Velocity Lab, and hope you enjoyed.